Test, test, test. Okay, nice. Okay. So hello, good morning, everyone. First of all, sorry, I think my voice is a bit different. Yeah, I have a sore throat as well. So yeah, if you guys feel sick, please do check. Go to your clinic because I think there's also I've been told that other section in other sections there's students that are positive COVID as well. I'm not sure if I'm positive COVID or not. I haven't checked. I will check after this, but hopefully not, because or else it's gonna be a big thing. I hope not. Okay, but if you do feel sick, please go to the clinic. Okay. And I've also been told that some of you guys cannot come today, which is fine because I'll just take the attendance for everyone for today. Okay. And today's class won't be too long. I'll finish around 11:50. Okay, on the first half today. Second half I'll let you guys off. Depends on you guys whether you guys want to do the exercise or because we will be finishing chapter 4 today. Okay, so I will give you guys the exercise for chapter 4 and you guys can do on the second half. So for today, we'll proceed with the last part. Wait, did I record already? Yes, I record already. Okay. Today we'll continue with the last part. A recording will be available later, so to those who cannot come today, I will give the link also. So for today, we'll continue to talk about still the Poisson distribution. It's still the Poisson distribution, but today we'll do a special property for the Poisson distribution, which is the approximation. Okay. For the Poisson distribution, as we see yesterday in the class, okay, we talk about how Poisson distribution is about the interval of time. Okay, any interval of time, if we have the mean, we can use the Poisson distribution. Okay, but here, since we have the Poisson distribution as an interval of time, we can also use it to approximate the binomial distribution. Okay, if you still remember, a binomial distribution is a distribution where you have two different outcomes. Okay, or yes or no, success or fail. Okay, so if the binomial distribution has a very large number of n, okay, which is the number of trial is very large, okay, which means that we can approximate it into some kind of interval. Okay, because there's there's a lot of trials for the binomial distribution, which means that we can use it as also as an average in an interval. Which means here, for a binomial distribution, we can approximate it using a Poisson distribution. Okay, so if x is a binomial random variable, okay, given an n and p, okay, you know that n is the number of trials and p or pi lah here. Okay, this one is pi. Okay. Then if n is more than 30, okay, more than or equal to 30, and np is less than 5, np is when you multiply n with p or n with pi. If these two conditions are satisfied, then these values are outside the range of the table, okay, because you cannot use the table anymore because n is not in the table and this thing will also not be in the table. So if these two conditions are satisfied, So we can use it. We can use a Poisson distribution. Okay, if you see here, if x follow a binomial distribution of n and p, which means we can use x also to we can use it. We can use a Poisson distribution with lambda here. Okay, so lambda we can approximate it using n multiplied with p. Okay, that's it. That's the concept here. Again, we can approximate a binomial distribution, approximate it using a Poisson distribution. Okay, so a Poisson distribution, we need to know what the mean is. So the mean here we will be using n multiplied with p. Okay. Okay, let's take a look at an example. Okay, here, okay, this is task 4.21 in your book. Okay, so given that x follow a binomial distribution, okay, with n equals to 500 and also pi equals to 0.003. Okay, and then we need to find the probability of x equal to 4. Okay, if you want to use a table, okay, if you want to find n equals to 500, okay, if you check your binomial table here, if you check the n over here, okay, so n here will only go up until the biggest value of n here is just 30. Okay, just 30. Okay, just 30. And p up here, the value of p is on the, okay, we want 0.003, but for p up here we only have the lowest is 0.001. Okay, so we don't have this value on the table. So what we can do is we can approximate using a Poisson distribution. First of all, if you want to check if you can approximate using a Poisson distribution or not, check the properties. Let's check the condition first. There are two conditions that you need to satisfy. First, if whether n is more than or equal to 30, and second is whether n multiplied by p is less than 5. So let's check that. We have n is equal to 500, which is more than 30. Okay, and here we have equal to 500, which is more than or equal to 30. Good. Okay, the first condition is satisfied. For the second condition, we need to check whether n multiplied by p is less than 5. So if we do n multiplied by p, which is 500 multiplied with 0.0003, 0.003, you will get the answer of 1.5. Okay, get the answer of 1.5. This 1.5 is less than 5. So the second condition is also satisfied. So once these two conditions have been satisfied, okay, we can use a Poisson distribution. So it will still be x. Okay, it will still be the same thing because we only approximate. We did not change anything. Okay, it will still be the same variable x. So x now we can approximate using a Poisson distribution. Okay, what is the mean? Okay, the mean will be n multiplied with p. N multiplied with p. So n multiplied with p, we get 1.5. So we have a Poisson distribution with mean of 1.5. So from here, you can just use your probability distribution, or you can also check the table. If you want to just use a probability distribution, then it will be easier. So remember that the probability distribution, okay, so for p x equal to 4 equal to e to the power of negative lambda. In this case, lambda is 4. So negative 4 and then multiply with lambda to the power of x. Lambda is 1.5. My god, what's wrong with me today? Sorry, yeah. So your lambda here is 1.5. okay, negative 1.5, okay, and then lambda is 1.5 again here to the power of x, so x is 4, okay, then divide with 4 factorial. Okay, this one is this your probability distribution for Poisson distribution. Okay, e to the power e to the power of negative lambda, and then lambda to the power of x, and then multiply with x factorial. So here you will get the answer of 0.0471. 0.0471. Okay, so that's how you get from the binomial distribution. Okay, and then you approximate it into a Poisson distribution. Okay, you also have mean which is equal to NP is 1.5. So you can just calculate that using this Poisson distribution. Okay, so you get this one. And for the second question, we want to find Px more than or equal to 5. Okay, P such that x more than or equal to 5. Okay, still we will be using this one. Okay, where x approximate as a Poisson distribution of mean 1.5. So here you can just use the properties as previously, which this will be equal to 1 minus P of x less than or equal to 4. Okay, so here you can just use as usual. So this one 1 minus Px less than or equal to 4. Okay, remember now that we are using the Poisson distribution. Okay, we are using the Poisson distribution. So you can check your table of Poisson distribution. In this case, x is 4, and the mean that we want to look at is 1.5. So take a look at mean first. So mean is 1.5. So mean is 1.5, and then we have x 4. Okay, x less than or equal to 4. This we have 0.9814. So here we have 0.9814. Okay, so here the answer will be 0.0186. Okay, so this is how you calculate lah for this one. Okay, we are not using binomial anymore because we already approximate it using a Poisson distribution. Okay, so you need to refer to your Poisson distribution table lah. Do not refer to the binomial distribution table because you will not get these values. Okay, but we are instead using this Poisson with mean equal to 1.5. For question 3, we have P of x less than 3. So when x less than 3, we also know that from the properties that this will become probability of x less than or equal to 2. Okay, probability of x less than or equal to 2. Again, this one we don't use a binomial distribution anymore because we already approximate it using a Poisson distribution of 1.5. Okay, which means here you still need to take a look at the table again. So mean is 1.5, and then you want to check when x less than or equal to 2, which here we will get 0.8088. 0.8088. So here we'll get 0.8088, okay, straight away. Okay. So far, any questions about the binomial distribution and the approximation? Questions? Okay. So to recap, we approximate binomial distribution using a Poisson distribution. Okay, when the binomial distribution here is the number of n is very large. Okay, if it's very large, then we can approximate using a Poisson distribution. So when n, how do we know it's very large? Okay, when n is more than or equal to 30, and you also need to check when NP is less than 5. Okay, you must check these two conditions first before you can approximate using a Poisson distribution. Okay, check these two conditions, and then if these two conditions are satisfied, then we can approximate using a Poisson distribution with mean equal to n multiplied with P. Okay, and then you just proceed with the Poisson distribution. Okay. Alright, let's take a look at example 4.22. For example 4.22, we have air airway flight from Kuala Lumpur to Johor Bahru is not on time 0.5% of the time. Okay, 0.5% of the time. 130 flights were observed. And what is the probability, okay, for this first question, that more than 4 flights are not on time? Okay, so here we know that this is a binomial distribution. Okay, how do we know this is a binomial distribution? Because the question wants us to find the probability that more than 4 flights are not on time. So there will be two different outcomes here, whether the flight will be on time or the flight will not be on time. Okay, there is two different outcomes. Okay, if it is a Poisson distribution, we will talk about some interval. Okay, we will talk about the mean on some kind of interval. Okay, for example, last class we talk about the call. Okay, the phone call in 1 hour. Okay, that one we know that will be a Poisson distribution. But here, since we have the probability, okay, the probability and also number of n, okay, we don't have any interval here, so we know here that we are talking about a binomial distribution. So in this case, a flight is not on time 0.5% of the time. So 0.5% of the time is the probability that the flight is not on time. So this one we can it can be the pi lah. It can be the pi. Okay. And x is the when flight is not on time. Okay. Flight not on time. Okay. And then 130 flights were observed. So this is your n. Oh, n. This is your n. Okay. So we know here that n is 130, which is big. Okay. So check the conditions. Check the conditions. So the first condition, whether we have here n equals to 130, and the first condition is n must be more than or equal to 30. So 130 is definitely more than 30. Okay, so the first condition is satisfied. The second condition is we want to check whether NP, okay, NP must be less than 5. So check whether it is less than 5. So we have n equals to 130. And then P, so what is the value of P? Okay, P is not 0.5. Okay, P is not 0.5. Why? Because here we have percent. Okay, it is 0.5%. So 0.5%. So percent, you know, percent means over 100. So here you can write as 0.5 multiply with, divide with 100. Okay, 0.5% is not 0.5. So this one, if you calculate this, you will get the answer of 0.65. 0.65. Okay, so 0.65 here is your NP, which is less than 5. Which means the second condition is also satisfied. So we can approximate this binomial distribution problem using a Poisson distribution. Okay, so x now, okay, x is the flight not on time, will now follow a Poisson distribution with the mean of NP. So what is NP? NP is 0.65. Okay, so now we'll just solve this question using this one lah. Okay, using this one, x follow a Poisson distribution of 0.65. Right, so what is the question one? So we want the probability. Okay, so we want the probability of that more than 4 flights are not on time. So we have flights are not on time. That is more than 4. Okay, this is what we want. Probability of x more than 4. So okay, from this point you can just continue as how you usually do previously. So just check your properties. So this one will become 1 minus p of x less than or equal to 4. Okay? P of x less than or equal to 4. So if you check your what is it? Poisson distribution table, okay, you have 0.65. Okay, you have a mean of 0.65, so you don't have 0.65, you have 0.6 and 0.7. Okay, which means that 0.65 is directly in the middle here. Okay, so 0.65, hold on. Okay, you have okay, you have a lambda of 0.65, right? So your 0.65 lah. Okay, 0.65 is exactly in the middle here. It's 0.65. So if you want to see the values, so here is 1 minus. So when x equal to 4, which will be between 0.9996 and 0.9992. Okay, so it is between these values. So since 0.65 is directly in the middle, what you can do is just to take the average. Okay, take the average. So the average of 0.9996 and 0.9992, what you can do is just 0.9996 plus with 0.9992 divide with 2. Okay, divide with 2 to get the average. So here you'll get 0.9994. Okay, which means your probability of flights more than 4 that is not on time is 0.0006. Okay, so this one, if you need, yeah, okay, this one is 0.65 over here. Okay, usually in your test or your exam, the exact value will be given. But in this case, if the value is not given, in this case your lambda is not in the table, but instead it's like in the middle. If it's in the middle like this, you can find the values by taking the average. Okay, since 0.65 is between 0.6 and 0.7, what you can do is taking the average of the values. Okay, why this value? Because this one is for x equal less than or equal to 4. Okay, so take the average of these two values, so you'll get 0.9994. And then you just minus as always lah. So 1 minus 0.9994, you will get 0.0006. Okay, for the second question, we have probability that between 8 and 15 flights are not on time. So we can write this as probability between 8 and 15 are not on time. Okay, so if we check again your properties, we can rewrite this as probability of x less than or equal to 15 minus with probability of x less than or equal to 7. Okay, and remember that our x follow a Poisson distribution of 0.65. Okay, so check again your table. Table Poisson distribution. Okay, so here where is the okay, we have lambda equal to 0.65. Okay, we know it is in the middle here. But where is the values for x equal to 15 and x equal to 7? Okay, less than or equal to 15, or x less than or equal to 7. So for x less than or equal to 15, if we don't have it here, we don't have it here because the value will be big enough, okay, that the probabilities that will be very close to 1. Okay, I repeat, the value of x is so big, okay, for this mean, that the probability for x less than or equal to 15 is very close to 1. Okay, see here, down here will be all 1. Okay, so the value will be very, very close to 1. So we can just approximate it. Just write 1.0000. Okay, because the value will be very close to 1. Then minus with x less than or equal to 7. Okay, same goes here. We have number 7 here, but we don't have the probability written here because the value will be close to 1 as well. So what we can write here is also 1.000. It's not exactly 1, but it will be very, very close to 1. Okay, it will be 0.00000. Sorry, it will be 0.99999 something. Okay, so the value will be very close to 1. So if we minus this thing, it will just become 0. It will be very close to 0. Okay, if you actually do the calculation, it will be 0.00000 something lah. Okay, but for this case, we can just approximate it. Okay, very close to 0, which means that the probability that 8 and 15 flights are not on time, okay, is almost close to 0. Okay, why is it almost close to 0? Because our mean, okay, remember that Poisson is, we have mean here, mean is 0.65. 0.65 is very, very small. It's even lesser than 1. Okay, so to find something that have a probability that is more than 8, okay, more than 8 or even 15 in this case, the probability of that will be very small, okay, to get, because our mean is just 0.65. Okay, so that's why here our answer is very, very close to 0. Okay, any questions here for task 4.22? Okay. If there is no question, I hope you guys are in the right place to do some exercise. So you guys can try task 4.23 and task 4.24. This is task 4.23. The question is almost the same. We'll discuss in a bit. Okay, I'll give you guys around 5 minutes to try this question. 5 to 10 minutes. Okay, we'll continue on discussing task 4.23. Okay, so for task 4.23, we have this question. So there is 0.1% chance that the shipment of transistors from a supplier is defective. A factory will only accept the shipment if there are not more than 2 defective transistors in a shipment of 2000 transistors. So what is the probability that the factory will accept the shipment? So for this question, okay, so what's the probability that the factory will accept the shipment? Okay, so how will the factory will accept the shipment if there are not more than 2 defective transistors? So what we can do is we let x be the number of defective transistors. Okay, x be the number of defective transistors. And we know that the transistor can either be defective or not defective, right? So here we will use a binomial distribution. So what we have here is a binomial distribution of n equals to 2000 and pi equals to 0.1%. Okay, 0.1%. Again, your pi is not 0.1, but instead 0.1 over 100, which is 0.001. Okay, don't get confused, yeah. Don't forget that we have percent. So if you have percent, you must divide by 100. So here will be 0.001. Okay, this is your pi. So since your value of n is very large, the value of n is very large, it will not be in your binomial distribution table. So what you can do is you can approximate. Okay, you can approximate using a Poisson distribution. So to approximate, you must check the two conditions. Okay, so n must be more than or equal to 30. Okay, so this one is 2000. So 2000 is definitely more than 30. So the first condition is satisfied. The second condition we must check is whether NP is less than 5. So here NP is equal to 2000 multiplied with 0.001. So here if you calculate it, you will get the answer of 2. So NP is equal to 2, which is less than 5. So if it's less than 5, then the second condition is also satisfied. So what we can do is we can approximate x to a Poisson distribution with mean of NP. So our NP is equal to 2. Okay, so now what we want to find is what is the probability that the factory will accept the shipment. Okay, and how will they accept the shipment if there are not more than 2 defective transistors. So what we need to find is the probability of x, so x is defective transistor, is less than or equal, not more than, okay, not more than 2 is also including 2. So what we need to find is the probability when x is less than or equal to 2. Okay, the number of defective transistor is less than or equal to 2. So until this point, you can just continue as always. Okay, so we have x that follow a Poisson distribution with mean of 2. So you can check your Poisson distribution table. Okay, your lambda is equal to 2. Lambda is 2, and your x that you must find is x less than or equal to 2. So it is just 0.6767. 0.6767. Okay, so this is the probability that there is no more than 2 defective transistors, and it is also the probability that the factory will accept the shipment. Okay, so 0.6767. Or if you want to also change it into a percentage, you can just multiply with 100. So that is a 67.67% chance that the factory will accept the shipment. Okay, I think here a bit confusing part is to define this question, okay? Because the question is just like a block of text, right? So you need to take out the information from the question, okay, and then understand what does the question want. Okay, in this case, the question stated that it is in a binomial distribution. So because of in binomial distribution, and because the number of n is very big, so we can approximate using a Poisson distribution. Okay, and then you need to calculate using the Poisson distribution. Okay, this here you need to understand the question a bit more. Okay, just take out the information first and then do what you must do. For task 4.24, okay, task 4.24, where is it? Okay, factory access produce components of which 0.1% are defective. Okay, again, if you see 0.1%, we know that this is 0.001. Okay, 0.1 divided by 100. And the components are packed in boxes of 800 and a box selected at random. Okay, so again, similarly as previous question, we have a component that is either defective or not. So we know that we are working with binomial distribution here. And we have a pi of 0.001 and also n equals to 800. Okay, we know that this n is very big. Okay, since n is big, we can approximate into a Poisson distribution. So n is already more than 30. Okay, so the first condition is satisfied, and then you check your NP. Okay, in this case NP is 800 multiplied with 0.001. Here you have 0.8. So again 0.8 is less than 5. So the second condition is also satisfied. So the first question wants us to find the probability that the box contains at least 12 defective components in the box. Okay, so what we can do is X is a defective component. Defective component. Okay, so instead of using a binomial distribution, with with 800 and 0.001, okay, we can approximate it using a Poisson distribution with mean NP. So NP is 0.8. Okay, so what we want for question 1 is the probability of X less than, not less than, at least. So at least means more than or equal to 12. Okay, probability of at least 12. So X is more than or equal to 12. So if you check your properties, okay, this one's for question 1. If you check your properties, you will get 1 minus, you need to find 1 minus P of X less than or equal to 11. So here, if you check your Poisson distribution table again, so your lambda is 0.8. And your X is, what you want to find is X less than or equal to 11. So there's not 11 here. There's not 11 in the X row, X column. So you know that it is down here. Okay, 0, 1, 2, 3, 4, 7, 8, 9, 10, 11. Okay, so it is more than 1. More than 1. So it will just be 1 minus 1.000 lah. Okay, it is close to 1. So the probability of X more than 12, okay, more than or equal to 12 is just very close to 0. Okay, you can just write as like this. It's approximately 0. The value is very, very close to 0. That the answer is approximately 0. For the second question, so we want to find the probability of there are 3 to 9 defective components in a box. Okay, you know X is a defective component, so there are either 3 or up until 9. Okay, so X is between 3 and 9. So if you forgot, you can just check your properties again, but please make sure you memorize how change from this one into the other form lah. Okay, because in your exam the properties will not be given. Okay, so you need to memorize it. So this one would be probability of x less than or equal to 3, less than or equal to 9 minus with probability of x less than or equal to 2. Okay. If you don't remember how to change from this to this, please make sure you do a lot more exercise, because I think doing more exercise will just make you get used to it more. So here, Px less than or equal to 9. Okay. So your lambda is 0.8. So you don't have x less than or equal to 9. So it will just be approximately 1. So 1.0 minus with when x less than or equal to 2. So 0.8 x less than or equal to 2 is 0.9526. So approximately 1 minus 0.9526. So your answer will be 0.0474. Okay. So that's how you do your binomial approximation using Poisson distribution. Any questions about task 4.23 and task 4.24? Okay. So the main point here is if you see a binomial distribution that has a n, as a big n, okay, and more than 30, so you need to check these two conditions, and then we can approximate using a Poisson distribution. Okay, and then you just proceed using the Poisson distribution. Okay, and with that, we are done with chapter 4. Okay, we are done with chapter 4, and there's only one chapter left, which is a very short chapter, which is the normal distribution. Okay, I'll see if I can enter chapter 5 tomorrow. Okay, chapter 5 is again about the normal distribution. Okay, normal distribution, we're going to talk about the continuous variable. Okay, because in this chapter, chapter 4, we only talk about the special probability distribution for discrete. Okay, and then in chapter 5, we'll talk about the continuous distribution. Okay, right. So for this first half, that's all for today actually. And for the second half, what I want you to do is we will not meet. Okay, we will not meet here, but instead, hold on, yeah, chapter 4, chapter 4. Okay, I'll give you guys this exercise for chapter 4. But you can do it, and you can also send it as an exercise. Later I'll create a place where you can submit it on the Google Classroom. Okay, so there's 5 questions. It's okay if you don't have to send it today. You can send it by say next Sunday. Okay, so you can still, if you didn't finish it today, you can still continue it until during the weekend. Okay? So this is just an exercise for you to understand more lah about this chapter. Okay, as I said before, you need to do quite a lot more exercise in this chapter, especially because the properties that you need to remember and also understand. Okay, so there's 5 questions here. I will share this in a group in a bit. Okay, so if there's no more questions, we can end the class for today. Thank you so much for coming. And again, if you feel sick, please do go to clinic and take care of yourself more. Okay. So thank you so much, everyone, and have a nice day. For tomorrow, sorry. For tomorrow, do you guys prefer online class or class face-to-face? I think I want to do more online class just in case, because in case I do get, in case I'm not still feeling well, and in case you guys also not well, is everyone okay for tomorrow to be online class? Tomorrow our class will be 9 to 11. Everyone okay, yeah? Tomorrow online class. Okay. So for tomorrow will be also online class. Okay. Tomorrow 9 to 11. Okay. So if there's no more questions, see you guys tomorrow online. Okay. I'll give you guys the exercise in a bit. Okay. Thank you so much for coming, everyone. Have a nice day.